Okay, so let's talk about ionic bonding. An ionic bond occurs between a metal and a non-metal, and we usually call any substance that's made with an ionic bond a salt. Okay, you need to remember this because later on I'm going to give you general reactions like an acid plus a metal gives you a salt and water. So an ionic bond forms between a metal and a non-metal, and you get what's called an ionic salt out of it. So one atom is going to lose electrons, one atom is going to gain electrons, and that makes them into an ion. So ions are attracted to each other with electrostatic forces. Remember, we've learned about electrostatics, opposite charges attract. And so because we measure charge in coulombs, they're sometimes also called coulombic forces. So electrostatic or coulombic forces, and this basically boils down to opposite charges attract. So the salt that we know is table salt, sodium chloride, and so sodium gets a positive charge, and if you look on the periodic table at sodium's numbers and then you look at this representation of its electrons, you can see here is the sodium with 2, 4, 6, 8 electrons in its outer shell. It's fooling itself that it's neon, so it's a very happy atom because it has got its full octet, the outer shell there. Okay, whereas chlorine here on the opposite side, chlorine did not have a full outer shell until it gained an electron. So electrons are negatively charged. So if you are a chlorine ion or a chloride ion more properly, the chloride ion has one negative charge. It gained an electron and it now has 2, 4, 6, 8 electrons in the outer shell. So one electron went from here to here, taken, not shared. So that is an ionic bond. The moment you have a positive charge and a negative charge, opposite charges attract. So metals usually give away electrons and become cations. They have a high electronegativity. So remember we talked about the definition of electronegativity. It's one of those definitions you have to know. But metals give away electrons and become cations. So cations are positively charged, which means the other ion is an anion and it's negatively charged. But cations are positively charged. So a cation is any positively charged atom or group of atoms. Isn't static electricity wonderful that all those balloons can stick to the cat? Okay, so now with a molecule, you can get like H2O, and there are 3 atoms. Finish and Klar, that is the molecular structure. With ionic bonds, we form what's called a crystal lattice. So you can think of a lattice as like a jungle gym. Here is a ball and stick representation of a salt, sodium chloride crystal, where all of the lines are bonds between the atoms. This is the same salt, sodium chloride, but this is now a space-filling representation as opposed to a ball and stick representation. So here, for every sodium ion, there's a chlorine ion. So one sodium ion in the red here and one chlorine ion in the green, and these two are attracted to each other through the coulombic forces. But what happens is coulombic forces are so strong that lots and lots and lots and lots of ions pack together into this crystal lattice. So when we say sodium chloride is NaCl, in actual fact, it's not like when we say water H2O, because you can get those 3 H2O atoms by themselves. But this sodium chloride does not exist as one Na plus ion and one Cl minus ion. It exists as this giant lattice, the ionic crystal lattice. So this ionic crystal lattice, they can have different structures, okay? So this is what the old textbook defines with the lattice. A crystalline solid has a rigid order, and its atoms, molecules, or ions occupy specific positions. And a unit cell is the basic repeating structural unit of a crystalline solid. So what this actually means is all metal salts, if you let them crystallize into perfect crystals, all the metal salts in actual fact have slightly different shapes, and it's based on the unit cell. So you can see this unit cell looks like a parallelogram because it's been pushed over. So it's like a prism of a parallelogram. So here's the unit cell, and here is the crystal solid that it will make, the crystal lattice. So there are 7 types of unit cells. You're just supposed to know these exist. You don't have to remember them. But like there's cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, hexagonal. If you go into geology, the study of rocks, this becomes important. But it's not that important for you. Just need to know that the atoms in a crystal lattice can arrange themselves in different ways. So simple cubic is close to sodium chloride, and I've got a picture of a hexagonal one as well in my slides here. So if you put salt, ordinary table salt, sodium chloride, under a scanning electron microscope, or even under an ordinary microscope, you can see that these actually look like square blocks that have grown on each other. Can you see here's one that looks almost exactly like a cube, and that's because the sodium chloride has that cubic structure, and it makes actually very square crystals. But if you see magnesium diboride, which scientists make for whatever science reasons, can you see here under the electron microscope, there are some that have not formed crystals, they're little balls, but there are some of them that form absolutely perfect little hexagonal crystals, and this is based on how the atoms arrange themselves. So the very structure of individual atoms makes crystals that we can see. Sometimes you can actually see salt crystals with your naked eye, but this one is a superconductor, so we won't be finding it in our kitchen. So this is 10 micrometers across this slide here, so 10 times 10 to the negative 6 meters. So it's quite small, but it's actually not that small. But you can see it's very clearly a hexagonal prism. Okay, what do we know about ionic compounds? They have high melting and boiling points. They are hard and brittle. When they are solid, they can't conduct electricity. Remember, all the electrons have been taken, not shared, between the atoms, and so there are no free delocalized electrons running around. But if you melt an ionic salt, they can conduct electricity. Sometimes this happens in industry because they've got really high melting and boiling points, but sometimes they do melt a salt so that they can conduct electricity through it. We see an example in grade 12. But what is the most important thing about ionic compounds? Ionic compounds dissolve in water. And when you dissolve an ionic compound in water, they can conduct electricity. When you dissolve an ionic salt in water, they form what's called an electrolyte. So we sometimes see in TV ads, go drink your sports drink, it's full of electrolytes. This is not quite the same, but it's almost the same. Our body actually uses a lot of electrical processes. So those ions that are dissolved in your sports drink are actually help your muscles working, and your muscles and nerves actually use ions and electricity for stuff to happen for your body to move. So it's another usage of the word, but we use it quite a lot in chemistry. The ions dissolve in water to form an electrolyte, which can conduct electricity. And if we ever get back to school, I will show you electrolysis, the splitting of a compound with electricity. You should actually know it from grade 8 and 9. Okay, why can water dissolve ionic compounds? It's all got to do with water is polar. So when we say water is polar, we don't mean it lives in the Arctic and the Antarctic. We mean it's got 2 poles at opposite ends, and there's a slightly negative pole and a slightly positive pole, and we use this Greek small letter delta. The Greek small letter delta is always used for charges. The capital delta, which is the triangle, we use it for change. So what happens is this oxygen, it's got a lot of protons in its nucleus. Opposite charges attract. This poor little hydrogen's only got 1 proton in its nucleus. These electrons go towards the oxygen because the oxygen is highly electronegative, and then that makes the electron cloud around this molecule be concentrated around the oxygen. So this end, this poor little proton in the hydrogen nucleus is left alone. This is slightly positive, and the same with this one. So that's why water is polar, and we know unlike charges attract. So this is how water dissolves things. If you have a look here, here's my salt crystal made up of sodium positive ions and chlorine negative ions. And we drop the salt crystal in the water, and along come all these cute little water molecules. And if you have a look at what's happening, if here's the chlorine ion, all the water molecules turn so that the slightly positive end is towards the chlorine, and they turn so that the slightly negative ends is towards the sodium ion. And when they do that, they can actually pull apart the crystal simply through the forces of attraction between unlike charges, and this is how the salt dissolves in water, because water is polar. There's a chemistry rule called like dissolves like, so polar substances dissolve ionic substances, and covalent substances dissolve covalent substances. Like dissolves like. Okay, and then the last form of bonding is metallic bonding. This occurs between metal atoms. So the atomic nucleus, that's the protons and neutrons, plus the inner core electron shells. Okay, so remember we've got core and valence electrons. So the nucleus is positive and the inner electron shells are packed into a crystal structure, and the valence electrons, the outermost shell electrons, can move around. So we say we have a positive metal ion core, and they have a sea of delocalized valence electrons moving around. And that's what forms the metallic bond. These negative electrons and the positive core sticks them all together. So they say the smallest particle is a positive metal ion, but they don't ask this a lot. And this is technically true, but we don't think about this a lot this way. And then you can join metals together in what's called an alloy. So you can mix together, say for instance, iron and nickel. And iron, nickel, and chrome will make you stainless steel. So steel and iron are different, even though steel is mostly iron. Steel is an alloy of iron and chrome and nickel, I think. Okay, and then you get brass, which is like copper and tin. And so these are alloys. They have different properties to the existing metals, but basically what's happened is the positive, they're all sharing their electrons, but the positive metal cores are packed into a network structure. So see, here's a visualization of it, where this orange blob here is the positive nucleus and the core electrons, and this fuzzy yellow out here is the sea of delocalized valence electrons. See here? Here's potassium 1s2, 2s2, 2p6, 3s2, 3p6. That's this. Okay? And then this 4s1 is this yellow sea floating around the metallic cores. So here's the positive core, here's the sea of delocalized valence electrons. So this is how it boils down. Chemical structure is split into ionic, covalent, and metallic structures. And these are giant crystal lattices. And these are also giant metallic lattices. These are ionic lattices. These are metallic lattices. And then if we look at the covalent structures, that splits into two. The giant molecular structures, okay, so like a diamond, where we've got and like quartz, which is huge. Or we have small simple molecules like water, but we can also get big molecules that have got like a lot of atoms in them, but they're still not a giant molecular structure. And there's this word polymer. We'll learn more about polymers in grade 12. Okay, and this is where we'll stop for now.